Okay, so we're going to start our first video for this unit. It's an introduction to arc length. This intro does assume that you read the pages in the book, pages 476 to 479, and that you've seen the proof and the formula to find arc length. I'm going to give you a quick rundown again though. It says to find the length of an arc of a graph if your formula is in the form y equals f of x, so y equals some sort of formula with x in it, then the arc length is found by doing the integral from x equals a to x equals b, so from the left side to the right side of the arc, of the square root of 1 plus whatever your function is, take the derivative of that function, and then square it, and take that integral with respect to x. Of course, in a similar vein, if you wanted to find the arc length of a function that was in the form x equals f of y, so x equals y this, y that, whatever, you would find your length by doing the integral from y equals c to y equals d of the square root of 1 plus, just take the derivative of the function, except your answer this time will have y, so we'll say f prime of y, and square it dy. So the nice part about arc length is in your book it's a lot more complicated. They expect you to do a lot of calculations, computations, and it takes a while, and we'll see one of those examples in a bit. On the AP test though, it's more recognition. It's can you recognize which one of these following is a formula for arc length. Sometimes they'll have you do a bit more. So we have 3 examples today, and we'll start with a fairly basic one. Our most basic example is here. Since this is my first attempt, all 5 multiple choice answers are in the same color as the example, and they kind of blend together, but we'll fix that later on. So it gives you the question, which of the following integrals gives you the length of the graph of y equals sine of the square root of x between x equals a and x equals b, where 0 is less than a, which is less than b. So just showing you which one should go first on your integral. A is smaller than b, a goes at the bottom. And then they give you 5 options. So we're going to work through this a bit at a time. You can recognize your function, and we'll start with that. Ultimately, we know we'll need to set up 1 plus the derivative of the function squared. So let's start with that. We'll just start with f of x, which they gave us as sine of the square root of x. And since we know we're taking the derivative, it's probably easier to look at it as sine of x to the 1/2. So we can take the derivative. We know we do the derivative of the outside first, cosine of x to the 1/2, times the derivative of the inside, chain rule never goes away, 1/2 x to the negative 1/2. But since we're going to be working with this a bit more, we should probably simplify. So we get cosine of x to the 1/2 times 1 over 2 times the square root of x. Yeah, and maybe instead of x to the 1/2, we'll change that to square root of x. Okay, and then we know we need the square of the derivative, so if we square both sides, it turns out to look something like this. Square of cosine square root of x times itself is just the cosine squared, 2 of those multiplying together. And if you multiply 1 over 2 times the square root of x times itself, you should find that it's 1 over 4x. 2 times 2 gives you the 4, square root times the square root, they undo each other, and we are left with this friendly looking equation. So if we set up a formula for arc length, we should see that the length is found by doing the integral from a to b of the square root of 1 plus cosine squared square root of x times 1 over 4x dx. And from here it's a simple matching game. We look back at our options and say which one matches this friendly answer. And it's definitely not A. B is close, they forgot the derivative of the inside. Not C, not E. It looks like D is our right answer. They just switched that 1 over 4x to the front, so we end up with D. And this seems to be the most common type of problem you'll see on an AP multiple choice test. A lot of times you'll see this with parametrics and polars, but we haven't done that yet, and when we do it, we'll go back to arc length. All right, second example. This one is being done to show you why the AP test doesn't have you do computations with arc length. It comes out of your book. It's actually problem 5, and it is one of your homework problems, so definitely good to pay attention to. They ask you to find the arc length from x equals 1 to x equals 8 on this very friendly looking graph. And let's see what we can do. We'll start the same way as the last one. We have our f of x equation, which is that 3/2 x to the 2/3. And then we know we need to take the derivative, so f prime of x. And the derivative to start looks pretty nice. You'll see that 2/3 multiplies times the 3/2. They undo each other, and it just leaves you with x. 2/3 minus 1 is that negative 1/3. And again, since we're going to be dealing with this a little bit more, we might as well write this in something that's more useful. So let's change that to 1 over x to the 1/3, just using the negative exponent. Okay, and then last but not least, we'll deal with the square of this. So we have f prime of x squared, and this becomes the whole fraction squared, and we know since it's division we can distribute the square, so it ends up looking like something 1 squared we know is 1, x to the 1/3 squared, and we know we multiply those exponents, so it becomes 1 over x to the 2/3. Alright, now let's get to the fun part. We are working for arc length, and we're going to use the integral from 1 to 8. That was in the given part of the problem. Square root of 1 plus 1 over x to the 2/3 dx. And here we run into a bit of a problem, because we're not allowed to distribute the square root with the plus inside, and we don't know how to take the integral of that. U substitution won't work, so we get kind of sad. The only way that we can distribute a square root, though, is if everything's in one fraction, or everything's multiplying together. So let's at least give it common denominators and see what we can do from there. So we end up with something like this. We get x to the 2/3 over x to the 2/3, okay, plus 1 over x to the 2/3 dx. And we have those common denominators now, so we can add together. And maybe it looks a little bit more simplified. X to the 2/3 plus 1 over the common. And although we still can't take the derivative of this, U substitution still isn't going to help us. We can at least distribute the square root and see what that does. Let's see. So we end up with x to the 2/3 plus 1 over square root of x to the 2/3 dx. And I think maybe it'll be easier to recognize this if we write it instead of the square root. We go back to that 1/2 power. And the reason that's interesting is because now we can see that these two are just a power to a power, and we know we multiply those together, which means we can cross reduce, and we end up getting something like this, where the top is staying the same, x to the 2/3 plus 1, still to that friendly 1/2 power, over just x to the 1/3. So we've actually gotten rid of the square root on the bottom, on the denominator. There's still one on the top though. But if we split this fraction, I think U substitution might actually come in handy now. What I mean by splitting the fraction is I'm going to keep that x to the 2/3 plus 1 to the 1/2 power out front, and then split the second piece. The denominator is 1 over x to the 1/3 dx. And the reason that's useful, and this is just a trick, it's something you'll start to look for, is if you have that 2/3 power and you realize if you subtract 1 you would get the negative 1/3, which would move it down to the bottom here. That is a really good candidate for U substitution. So we're going to do something like this. We're going to say let U equal x to the 2/3 plus 1, which gives us du equaling 2/3 x to the negative 1/3 dx. And simplifying further, it becomes 2/3 times 1 over x to the 1/3 dx. Now again, this is useful because we can see that this piece matches up here, and we have our easy u replacement, u substitution here. And honestly, since I've done all this work, we might as well change the limits of integration too. Remember, you don't have to, but they're pretty nice numbers, so might as well. Ends up looking like this, where we find u of 1, which is 1 to the 2/3 power plus 1. 1 to any power is just 1, so 1 plus 1 is 2. And then similarly, we have u of 8, which becomes 8 to the 2/3 power. We know we can rewrite that 2/3 power as the cube root of 8 squared. Cube root of 8 is 2, 2 squared is 4, so 4 plus 1 is 5. So we still have nice limits of integration. This was our little u substitution step here. So let's see what this ends up coming out to be. I think we will get being equal to the integral from 2 to 5, u to the 1/2. And then notice that I forgot to move my 2/3 over, so let's maybe throw that over here, where really this should be 3/2 du is equal to 1 over x to the 1/3 dx. So notice it didn't match exactly, so we had to take the reciprocal of that to get it over in front. So we have this piece being replaced by 3/2 du. Alright, and we can simplify this a bit further. We'll find that it becomes 3/2 integral from 2 to 5 u to the 1/2 du. And this isn't too bad now. 3/2 we can totally integrate, and we end up getting, well, 2/3 u to the 3/2 from 2 to 5. And we can tell that these two will undo each other. My pen decided to stop working. It'll probably jump back in a bit, or the whole program will just freeze. No big deal. It should still be there. There we go. U to the 3/2 from 2 to 5. And we saw before that these two will undo. So now it's just a matter of plugging in 5 and 2. So we end up with 5 to the 3/2 minus 2 to the 3/2. And with some practice, you'll see that the first one reduces to 5 square roots of 5. And the second one is the same with 2 square roots of 2. And that should match the answer in the back of the book. Again, it's a ton of work. There's a reason this doesn't show up on the multiple choice, but there are a couple practice problems. It's good algebra for you, and there are a few of those in the book. Alright, let's jump to our last one. Last one is also a multiple choice question. It says 2005. I have a feeling it's probably 2003, maybe 2008. Those are the ones that we get access to in terms of tests, but this is from one of the tests. I like this problem because it's a little bit more than just can you recognize the formula. It has you do a little bit of calculus too. So you get the length of a curve from x equals 1 to x equals 4 is given by our normal arc length formula over here. And then it says which of the following could be an equation for this curve. So you really have to work backwards. It's saying that you had some equation, you took the derivative, you squared it, you created your arc length formula. Now what was that curve? So let's set it up. We can do something like this. We know our arc length formula from 1 to 4 is going to be 1 plus the derivative of the function squared. And since we already have this piece right here, then that tells us that 9x to the 4th is going to be equal to f prime of x squared. Alright, we know that these two pieces have to be equal. So let's just see if we can isolate f of x. First step isn't too bad. We're going to take the square root of both sides. So we end up with f prime of x equals 3x squared. Now be careful here. I'm not sure about the curve, but we know that whenever you introduce a square root, we have a plus minus. I'm just going to work with the positive for now, and I'll show you what will happen if there was a negative later on and why it wouldn't be that answer. But we'll just start here. So just dealing with the positive 3x squared. We have f prime of x, and we know if we want to get back to f of x, back to our original equation, we'll need to integrate both sides. So integrate dx. And we know that this will just come out to be f of x equals, well, 3, so we have x cubed. That's pretty. Indefinite integral, though. There are no limits of integration here, so we need that plus c. So this isn't a final answer. We need to actually figure out what our plus c is to get an original equation up here. Notice none of these have plus c's. How can we do it? Well, it seems like I forgot part of my problem in that it says there is the point 1 comma 6 on the curve. So we are actually going to use that point 1 comma 6 to figure out our c. We know that when we plug 1 in, we should get 6 back out, which tells us that c equals 5. So resubstituting into our equation, we end up with x cubed plus 5. And this ends up matching, it looks like B here. Okay, so that's really all there is to it. I did say we'd go into a brief discussion about why that negative didn't work. So let's jump back over here and let's assume that when we took the square root, f prime of x ended up equaling negative 3x squared. The steps are still the same. You can integrate. Okay, and then you end up with f of x equals, and then this one's very similar except now it's negative x cubed plus c. Bring the 3 down, you get that negative 3. Plug in the same point, 1 comma 6. So we get negative 1 cubed plus c is going to have to give us 6 back out. So we end up with 6 equals negative 1 plus c, which tells us that c is 7. And you substitute back in, you say, okay, well that tells us that f of x has to equal negative x cubed plus 7. And that seems perfectly reasonable. I have a feeling if you checked it, it would work out. Except if you look for a through e, there is no negative x cubed plus 7. This one's pretty close, but they gave you that 6. So the only one that actually works up here is B. As always, if you have any questions, just send me an email, and hopefully this was useful.